All right, so here's the start of the lesson. The periodic table is going to be a resource we're going to use for the rest of the semester, and it's important that you guys know not just being able to tell characteristics of one element, but being able to look at the periodic table and determine different trends from the table. Now, the table I just gave you is not exactly the same as it once was when it was first made out to be. The first periodic table is the Mendeleev periodic table. Now, back when Mendeleev was alive, it was, over 100 years ago. And he was the first person to arrange the elements in this periodic table, and it was based off of properties. Okay? We're going to talk about some of those properties today. He revolutionized the way that we organize chemistry. A couple of years later, we have my Uncle Moseley. Now, my Uncle Moseley, he has really bad OCD. And so he decided that he was going to rearrange the periodic table based off of a thing called atomic numbers. Now, it's my understanding you guys have learned about atomic numbers before. Is that true or false? Okay. Atomic numbers, remember, those are the top numbers on each of your element cards. That's what I call them. Each square on the table is an element card. That top number is what Moseley used to organize the periodic table. Now, just a pop quiz. Does anybody remember what the atomic number also means for an element? It determines how many of these it has. Protons. Yeah, protons. So that's how Moseley organized the periodic table, and that's the periodic table that we use today, is Moseley's periodic table. Now, we've added elements to it since then because we've discovered new elements. Most of those elements are going to be in row 7 of your table, possibly in row 6, but mostly in row 7. The other 3 things on the, 5 things we'll talk about here in a little bit. The metals and non-metals part, make sure you write those 6 characteristics down, because I'll tell you right now, all 6 of those are on your quiz on Friday. Okay, being able to determine which ones go to a metal, which ones go to a non-metal. Oh. How's everybody's first day of school, by the way? Well, first day back. Hopefully it was good. So what?
So long.
It was long?
So
I thought it was kind of short, but maybe that's because I'm the baby around here. Who's watching a video right now? That is astronomically loud. That would give me a headache, like personally. That's deafening. Something that I did at my old school that I'm going to let y'all decide on whether or not you want to do, because it will give you more in-class time to work because of how long it takes y'all to write. Something that my old kids wanted to do was they decided they wanted to write the introduction slides at home ahead of time, because that way they got more work time in class to do homework and things. So is that something you guys want to do, or would you rather just write them in class? It doesn't matter to me one way or another.
In class.
Okay. Sounds good. Also, you can find these slides on your Canvas page, so if I'm moving too quickly and you don't get everything written, they're there. Am I good to move on?
Took 5 seconds after you.
Oh, you're still typing.
No,
2.
Hey, John, did you get that on Red Cup Day?
What?
yeah.
I got 3.
Oh, under 1.
Now, the reason I got 3 is I used to, so at my old school, I had 2 friends, and so I would be the Starbucks picker-upper because I lived close to it. And so,
Close to the Starbucks.
I did. Like within 5 minutes.
You still live close to it?
You did? Not now. Sorry, I moved the trash can.
That's fine.
I'm not actually sorry, I really. Okay, can I move on now?
Yeah.
Alright, so, I'll be honest, the rest of this, we're drawing. So hopefully, you guys are good artists. Now, the good news. If you are a responsible young person, you can do all of this directly on the periodic table I just gave you. Okay, that's why I gave you a paper copy. If you're not responsible and you feel like you might lose it, then I would kind of redraw the shape of the periodic table on your here.
Yeah, no worries.
Whoa.
So I'm going to go ahead and redraw the table here.
Did you say that? Oh my god. Like that's up.
All right, here's the periodic table in a nutshell. Does everybody agree with me? It looks kind of like that, right?
Yeah.
Now yours will have your squares and your boxes. I'll go ahead and move on those. Okay. Now it looks a little more accurate. Yours is also going to be split into some rows. I left off hydrogen and helium. But I'm not going to go all the way down in the rows for the sake of time. I'm just going to do the rows over here. Okay, 7 rows. Does everybody agree with me? Count yours. Make sure you have 7 rows. Not including the 2 rows at the very bottom that are out in no man's land on their own little island. We don't care about those right now. We'll talk about them later. But the main table, you have 7 rows. And then it should be listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Does everybody agree?
Yes.
Okay. So here are some trends that I need you to know. The first one that we're going to talk about is just group names. Group names. Groups are how we can determine what elements will act similarly to one another. Now, groups are also called families. Think about you looking at your mom and your dad. You share characteristics of them, right? You're kind of like a around 50-50 split of your 2 parents, okay? That's just genetics. Well, elements are kind of the same way. Only in families, they're not necessarily derived from each other. We just use them as descriptions. What that means are all of the elements in the same group have similar properties. Now, groups are columns. Families are columns. Groups, families, and columns are all the same thing. Whichever one you want to remember is great. Okay, you can pick. I will typically refer to them as groups because that's just how I learn. But groups, families, and columns are all the same thing. So, the first group, this guy right here, his name is the alkali metals. The alkali metals. These guys are superbly reactive. These guys will react with air. The simple amounts of oxygen in the air is enough to make these guys go boom. Water. It's enough to make something, if they touch water, boom. Elements in here, you have hydrogen, okay? You have, what else is in there? Sodium. I'm probably skipping a few, it's okay. Lithium.
Magnesium.
Magnesium's not in that one.
Oh.
You have francium. Francium's one of the most reactive elements in the periodic table, okay? Have you ever heard of somebody putting sodium in water? What does it do?
Explode.
It explodes. Hopefully, I'll be able to order some sodium, and so we can do that, and we can put some sodium in water later on in the semester. But, moral of the story, the alkali metals. Hey, this group is called metal, the alkali metals. So what do you think every single one of these elements are, metals or non-metals? They're metals, right? It's in the name. Like, I can't make that any easier, right? The second group, this second column, these guys are still reactive. They're not as reactive as these guys, but they're still pretty reactive. These are the alkaline earth metals. Now the alkaline earth metals, like I said, not as reactive, but most of them can be found simply within the earth. Okay? Magnesium's in that category. Calcium's in that category. Okay? Strontium and barium. Okay? All of these you've probably seen before, or you've ingested them before. I know you've had calcium. Do you put creamer in your coffee?
Yeah.
You're drinking calcium. Okay? Anybody who had milk this morning, calcium. Some of you have to take magnesium supplements. Okay? I've had to before. Those are some of the things that are natural that we just need in our bodies to survive. Cool? Now, barium and strontium, those we don't necessarily need in our bodies. So if those get in our bodies, we're going to blow up and it's not going to be a fun day. However, the guys at the top are the beast. Cool? You guys have no energy. Like, I feel so bad. Like, I feel like I'm just ranting on. Okay. In the middle, these guys, this is groups 3 through 12. These are transition metals. They're called the transition metals because they can actually change states. They change what we call charges. There are several different species of each element. For example, with iron, there can be iron 2, iron 3, or iron 4. Okay. Or you have nickel. You can have nickel 5, nickel 6. We'll talk about more about those 5s and 6s, 1, 2s, and 3s more next unit, but that's where the word transition comes from. These guys are not very reactive. Anybody wearing jewelry right now? Okay, do you have gold jewelry on? Silver? Say it. If you're wearing silver jewelry, is it burning your skin at all? Or is it like making you irritate? Not really, right?
No.
The idea is not really. If silver was a super reactive element, we couldn't wear it as jewelry because it would react with the things in our skin or it'd react with the stuff in the air and it can harm you. These guys are pretty non-reactive. Now, they will still react under certain circumstances, but much, much less reactive than these two guys. Okay, cool so far?
Yeah.
Let's go over here. So this is technically column 13. Okay, column 13. I guess I didn't label these. This is 1 and this is 2. Right there. Column 13 over here. This is where the naming part gets a lot easier. Over here, it's kind of foreign, alkali and alkaline. You've never heard of those words before. This is where things get easier. We are starting to get into the range of the nonmetals. Okay, we love nonmetals in chemistry. They make our lives a lot easier in a lot of different ways, and we use them for a lot of different principles and practices. In fact, almost your entire almost your entire body is made up of a non-metal, carbon. Okay? All living things have carbon in it, made out of carbon. And they come from the non-metal group 14, which we'll talk about here in a minute. The name for column 13, hey, what's the top element in there? Boron. Somebody said it. The fact that you knew that is crazy. Good job. Hey, column 13, it is the boron group. Some of you act like boron, but change the B to an M. I really thought that went over y'all's head, and I was like, oh, maybe that wasn't as funny as I thought. The boron group. That's a lot easier, right? Because if you can tell me that the first element in column 13 is boron, easy enough. It's the boron group. Column 14. The top element in there is carbon. What do you think the name of that group is?
Carbon group.
The carbon group. I read talk about the reactivity of 13. Hey, 13, very much not as reactive as any of these guys. Column 14, these guys, they will react. But for the most part, they're pretty stable. Okay? They are the exact middle land in terms of reactivity. Everything points towards carbon in terms of reactivity, with the exception of this guy, which he's special. We'll talk about him in a minute. What's the top element in 15? Nitrogen. What do we think that element or that group is going to be called? The nitrogen group. What about 16? Oxygen group. Now what about 17? What's the top element?
F.
Fluorine. So what do you think the group is? Nope, you're wrong.
Not the fluorine.
It is not the fluorine group. Fluorine is crazy. It turns out that the group 17 nonmetals, they're special. These guys are deadly.
Deadly?
These guys are deadly. Hey, how many of you guys brushed your teeth this morning?
Me.
Hopefully all of you. How many of you guys used mouthwash either last night or this morning? Ooh, okay, not so many of us.
Yeah, you did.
Hey, what special thing is in toothpaste and mouthwash?
Fluorine.
Fluoride. Fluoride is the ion version of fluorine. We're going to talk a lot about fluoride next week. But do you know why fluorine is in those things, toothpaste and
Kills
mouthwash?
bacteria.
It kills bacteria. It's a killer. Fluorine's a killer. That's why you spit it out. You don't swallow it. Because if you swallowed it, now if you swallow mouthwash once or twice, in your life, you're fine. But if on a daily basis you were just downing mouthwash,
Dead.
you're done. Dunzo. Kaput. Right? Wraps. It's deadly. Its entire purpose is to kill bacteria and germs that are growing on your teeth and in your mouth. The next guy in there, below fluorine, is Cl. Does anybody know what that one is?
Chlorine.
It's chlorine. Ever heard of chlorine gas?
Mm-hmm.
What does that do?
Explode.
It doesn't explode. It kills. Done. Dunzo.
Airball.
You've probably heard of people making chlorine gas at home by mixing bleach and ammonia. Or different cleaning supplies and cleaning products come together, they make chlorine gas. So have any of you guys actually ever cleaned your own bathroom? Okay, if you've ever cleaned your bathroom, have you ever been mixing different cleaning supplies? You start to get kind of lightheaded, a little woozy? Okay, well, I have.
I pick one thing if I use it.
I have. And that's because you've started to produce chlorine gas. And it makes you go super lightheaded and you can pass out and faint. And if enough is in there, you'll die. Okay? And the same thing goes for everything below that, from bromine to iodine and so on and so forth down the list. Okay? It gets deadlier as you go down, for the most part. Bromine gas is so deadly and so scary, it's literally just an orange gas. Like, it just looks like liquid death. Just through the air, okay? It makes the upside down look happy. That's a Stranger Things joke, I don't know. Has everybody watched season 5 already? The ending is kind of crazy. I don't know if I like it or not.
Yeah, I don't.
I don't know if I like it or not. Okay, anyways, these guys, because they are the deadly guys, we call them the halogens. That looks really ugly. The halogens. Okay. Halogenet or halogenic. Have you guys ever heard that word? That means deadly if it's halogenic. Okay. And finally, you have group 18. Anybody want to guess what the name of group 18 is?
Noble gases.
The noble gases. That's one everybody knows.
Cool.
The noble gases. Do you know why they're called noble? These guys are completely unreactive. They do not react with nothing except for very, very select circumstances. Another word for that is the word inert. Inert means non-reactive. Sorry. Those are the names of all of the groups on the table. Now we need to talk about rows. In my opinion, rows are the hardest thing I'm going to teach you today. There's 7 of them. That's it. There's row 1, 2, 3, 4, 5, 6, and 7. That's it. That's their names. I'm being serious. Their names are literally row 1, row 2, row 3, row 4, row 5, row 6, and row 7. Okay? I was just being sarcastic about them being actually hard. They're not hard. It's just literally 1, 2, 3, 4, 5, and 6. The groups, if you can remember the groups, you should be fine. Okay? Now, one thing that I will almost guarantee ask you on the quiz is I'm going to ask you, what is the halogen that's in row 2? So you'd have to know, okay, group 17 is the halogens. Row 2, I'm going to go down to the second row and kind of like a grid. You just match them up, okay? Like a battleship grid. So far, so good? Cool. All right. The next thing I want to do is talk about metals, nonmetals, and the things in between. Okay. There's 3 different types of elements. We have metals, nonmetals, and those things in between. Those things in between, we call them metalloids. Metalloids are exactly in the middle. Okay, we use them to differentiate between the metals and the nonmetals. I'm going to start with the metalloids because it will make your life easier. Okay. Have you guys ever heard the term the metalloid staircase? Okay, draw where I draw. In between boron, you're going to have a little line. Those 2 elements that line separates is boron and aluminum. And then I'm going to draw another line. And I'm essentially going to form a staircase. Sorry, that should line up with iodine. And I'm going to fill in those elements for you. So you'll have silicon, germanium, arsenic, tin, tellurium, and PO. Kung Fu Panda. Get it? 'Cause it's Po. Me, when I find out the whiteboard I spent $300 on isn't magnetic. Oh well. Me, when I've gotten 3 emails in the span of 5 minutes. Okay. These guys are your metalloids. There's one exception to this rule, and it's important you know this exception because it's on your quiz. The exception is aluminum. Anything touching this staircase, including boron, is a metalloid. Okay? Aluminum, however, is the only one that touches that staircase that is just a metal. Y'all have seen aluminum foil, right?
Yeah.
For those of you that haven't ever seen aluminum foil, first of all, you live under a rock. But you cannot tell me that this does not look like a metal, right?
Yeah.
Definitely a metal. It's shiny. You put it in a microwave, what happens? It sparks up because it's a conductor. Okay. Now, that should give you a hint. Everything on this side of the staircase, I'm just writing in the middle because that's where I have room, but it includes all of this stuff too. Anything on this side of the staircase is a metal. All the metals are on the left-hand side of the staircase. Which means if everything on this side is a metal, well, what's going to be on this side? The non-metals. The non-metals. What's up?
Does the staircase go all the way down, or does it stop?
It stops here with PO.
Okay, got you.
So what would LV be?
We won't talk about that. It's too ambiguous for y'all. It can be a lot of things. Honestly, the elements in the elements in row 7, we will almost never talk about, and that also includes row 6. After everything after bismuth in terms of atomic number, we probably won't talk a lot about. How do we feel so far?
Good.
Good. All right, there's a few more trends I need to talk about, and these are the 3 guys at the very bottom of your introduction slide. The first one I'm going to talk about is atomic radius. How many of you guys, have all of you guys taken geometry or are currently taking geometry? One of the two?
Yeah.
Radius, when I say radius, what does that make you think of?
Circle.
It makes you think of circles, but it makes you think of circles, yes. It makes you think about the distance between the center and the outside of the circle, right?
Yeah.
The radius. Chemistry is the same way. In an atom, you have a nucleus in the middle and you have a bunch of rings that go around it. Now, that's not entirely true, but that is a good 2-dimensional shape. Atomic radius is the distance from the nucleus to the very most outside electron. It's based off of the pull from the positive protons to the negative electrons. Okay? What I need you to know is that atomic radius increases as you go down and to the left. With francium having the largest atomic radius, helium has the least. The largest atomic radius is francium. The reason that francium has the largest atomic radius is it has 7 different rings go around it. And that very last ring only has 1 electron that's in it. That's not a whole lot of negative charge for the protons in the very middle that are miles away to reach onto. Now, there's also this concept called shielding that I need you to know. Another reason that atomic radius is so large for francium is there's so many electrons that are blocking those protons. 1, 2, 3, 4, 5, 6, 7. There's so many electrons, this is a horrible drawing, but it's because I don't have a whole lot of space, that are blocking out that pull from this guy. That's called atomic shielding. Shielding is inner electrons blocking the outer electrons. Okay? Shielding is all of the inner electrons blocking the outer electrons. The second trend I need to talk about, which I would argue is the most important, is called electronegativity. Have you guys used electronegativity yet this year?
No.
Oh, okay. Interesting. Electronegativity is essentially the opposite of atomic radius in terms of the trend line. Electronegativity.
I'm having trouble connecting to the internet.
Okay, I guess Alexa's not
Take a
connected to
look
the
at the
internet.
help section
Um,
on your Alexa app.
Electronegativity is an element's desire to gain an electron. How easy is it for an element to gain an electron? The most electronegative element is fluorine, while the least electronegative is francium. There's a reason for that. What time is this class in?
55.
Okay. The reason for that, we'll talk about in a minute, because I don't want to overload your brain. But electronegativity increases from the bottom left to the top right. Hey, why did I not go all the way to helium? Well, that's because these noble gases, they don't want to gain or lose electrons. They're what we call stable. They're inert, which is why they don't really have electronegativities. They don't want to gain or lose electrons. Okay, the last guy that we need to talk about is ionization energy. I'm looking out of colors. That's not nice. Ionization energy is the exact same trend line as electronegativity, but this one goes up to helium. Ionization energy is the amount of energy it would require for an element to to lose an electron. We'll talk about why it goes up that way in like 30 seconds once you guys write that. Okay, here's why these trends exist. Every single one of these groups, those groups we just talked about at the beginning, they have those similar properties. These are where those properties come from. They're valence electrons. Properties are determined by valence electrons. And it turns out, I'm going to write this down here because it's where I have the most group. All of the elements in the first column, in the first group, they have one valence electrons. Have you guys used the word valence electron before? Oh my God. Okay. Okay. The word valence means outer, the very outside electrons. Those are the electrons we care about the most because those are the ones that are involved in reactions. Valence just means outside electron. Okay. Is that a good enough crash course? Valence just means outside. These guys are what determine the reactivity of an element. These guys all have one valence electron. Hey, how many do you think group 2 has?
2.
2 valence electrons. We're going to skip the transition metals because they have their own fancy rules. And we're going to go to column 13. How many do you think 13 has?
13.
Nope. 3.
Nice.
What about 14? That's 4. 15? 16? 17? And 18. All elements crave to get to 8 valence electrons. They want to hit 8. 8 means stable. Write that down. 8 means stable. All elements crave to be stable. Now, in chemistry, 0 and 8 are the exact same thing. Elements are happy to have 0 and they're happy to have 8. Okay, did that just hurt your brain?
No, like that.
You went like that, and that made me feel like I hurt your brain.
No, you didn't.
Okay. 0 and 8 are the exact same thing in chemistry. Because if I have nothing, it's the exact same as having everything. Okay? So, one valence electron, the way I need you to think about this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 7, 8, 6, 7. Anyways, so if I have one valence electron, am I closer to 0 or am I closer to 8?
0.
I'm closer to 0. So would it be easier for this guy to lose an electron or to gain 7?
Lose 1.
It's way easier to lose one electron for it to be stable, right? Hey, what's the charge of an electron? It's a minus. So if I lose one electron, what's my new charge going to be? It's going to be positive. Positive what? You lost one electron.
0.
So you become positive by, so like if I have, let's say I have 5 protons. Let's say I have 5 protons and 5 electrons, right? 5 protons, 5 electrons, that's a 5, not a 3. I know that's really ugly, I'm sorry. 5 protons, 5 electrons. Right now my charge would be 0, you're right. But what if I get rid of 1 electron? And so now I have 4 electrons. Now what would it be? It'd be positive by what? Positive by 1. Every single one of these elements has a +1 charge. Make sure you write that number and circle it. We're going to use these numbers for the rest of the year. +1. Hey, what about 2? If I have 2 valence electrons, is it easier for me to lose 2 to get to 0 or gain 6 to get to 8? Lose 2 to get to 0, so what's my new charge going to be? Positive 2. How do you think I feel? Skip 3 through 12 again because they have their own fancy rules. Come to 3. What do we think 3 is going to be? Positive 3. Okay, 4. 4 is different because where's 4 at? It's in the very middle. Do you think it's going to be harder to lose 4 or gain 4? It's like the exact same. These guys, we say are plus or minus 4. They can act as either one. Look at 5. Now we really need to think. Hold on, give me like 10 seconds, I'll finish. Look at 5. Is it easier to gain 3 or lose 5? It's way easier to gain 3, so now I need to come back over here. Originally I was at 5, now I'm at 8. What's my new charge going to be? 3, positive or minus? It's minus now, so I have more electrons than positives. Bye, have a good rest of your day.